laser pointer is going to be a little bit hard to see.
Yeah, I don't typically use a laser pointer.
We also
so
have, if you see that little white thing in the corner that has like the green light, that's the camera that's looking right at you.
Okay.
It frames you about this, about here.
Okay, so don't move too far away. I'll just stay here. It's easier.
We can track you.
Okay.
Okay, so if you want to move around
Okay.
that camera up there, well, it's directed right here, right
Okay.
now. We've got a joystick that we can track you around the
Okay.
room.
All right,
So
super.
if you want to do like cartwheels up the ramp, we can do that. Like
If I had that ability, I would be happy to,
whatever
but
you want, we can do.
Okay.
If you want us to.
Okay, sounds great.
Okay.
Perfect.
And then just relax and
Okay,
try
super.
to relax.
Yeah, nice.
You should have a little butterflies. Everyone does.
I feel like after so many of these presentations, I guess you still always get a little
You
bit.
always-
Then one slide in, you're like, I'm on with it. So,
Sure.
Yeah, great.
So if you want to turn this off for right now.
Okay.
And then.
As soon as I start, turn it back on.
Exactly.
Okay,
Exactly.
sounds great.
So other people are just going to be.
Okay.
We don't want everyone to be listening to our conversations
Yeah.
about everything.
That's what you think. Okay, perfect. I'll put that right there. All set. Awesome.
And
I keep track of time. They said keep it to like 45 minutes, try to.
yeah, so that clock is only. It's only.
Yeah, it's like 2 minutes past. That's pretty good though.
Well, no, it's also like.
A few hours off.
Yeah.
Okay, yeah, you're
Okay.
very right. I was only looking at the minute hand.
Right. So don't mind how off it is.
Yeah,
But.
You got it. But
yeah.
but I know, once it makes it back around to the top, that's near the end. So even though it is moving, right?
Yeah, it is
Okay.
moving, but it's. I think I'm gonna get a digital one for there. Like
Yeah.
it's so crazy.
No, that's like the one in between my offices. I don't feel like it's ever, you know how they say, oh, once a day. Oh, I guess once a day. But I feel like it moves so slow, like not at the right speed, that you can't even count on once a day.
I don't even want to take it down because it helps people like as they're going through the slides.
Yeah.
Because they can know like
Yeah,
when it
because
started.
at least it's starting on the hour, right?
Exactly,
That's not so bad.
Exactly.
That's not so bad.
So like I will get to the point where we'll get something that's gonna be a little bit more reliable, but alas, okay. Yeah, you're gonna do fine. If you have any questions, flag us down. If you want to like just wave to the left of say
Okay.
if they need you or
Sounds
something.
great.
So all right.
Okay, perfect.
The other thing that might crap, that fell down again.
Oh, this did?
Yeah. Try that.
Okay. Sweet.
Yeah, so what was he saying? If you need us, flag us down.
Okay.
Otherwise, do you need any water or anything?
Nope, I have one right there just in case, but I think I can make it through an hour without it, so.
Okay. You're gonna do fine.
Okay.
Tom's gonna introduce you
Okay.
beforehand.
Great.
He's gonna ask you a couple questions.
Okay.
And then you're going to.
On we go.
On we go.
Okay, perfect.
So I'm gonna give this to him because he just takes this and does
Awesome.
his thing.
I appreciate the help. Thank you.
Estonia's in the Baltic. Estonia, Lithuania, Latvia, and then right now we're scared.
You know, because I'm thinking back on the.
Yeah, it's nicer to have a.
I figured out you should work on it. And he wanted to put some social media or something that had three.
All right.
We got the three in the last decade or something.
Look at that, you got the clock going.
I know, I was like, oh, he showed me there's one up there.
I can't remember
So
what
maybe
church
that'll be.
it was.
What's
That
that?
was Estonia, Estonia's pretty good.
That sounds right.
Oh, good, good. I hope it worked. Sometimes I talk and I come back around, and then sometimes I'm like, did I come back around correctly? We'll see. Yeah, we'll see at the end.
So what do you just use to help one people?
So that's always really helpful
Why do you want to destroy?
when I get feedback like that.
Yeah, that's great.
It is.
Hopefully over 12 years I've gotten better.
I think it's
Oh. Okay.
So here we're testing this hand mic, and that's good?
And yours is?
Yep. Can you hear me? All right.
Thank you, everybody, for coming Wednesday night to the lab tonight, both here in the auditorium and at home by Zoom or on YouTube. Next week, Isabel DiStefano will be zooming into us from the Field Museum in Chicago. This is part of the UW-Madison celebration of Darwin Days. And she'll be talking about discovering the DNA Discovery Center, collections-based research in evolutionary biology, museum science communication, and outreach. So you can come in here because it's Darwin's birthday, 213th. He was born on February 12th of 1809. We will have a cake here, probably have some other refreshments. Won't have 213 candles, but come on in if you'd like, otherwise you can zoom in from home. On February 16th, in 2 weeks, Bob Schneiker will be here. He'll be talking about protecting groundwater from leaching soil contamination. And on February 23rd, Marianne Fairbanks from the School of Human Ecology will be back to talk about the design, innovation, and entrepreneurship angles of how she developed this new Hello Loom. It's a handheld loom that introduces people to the arts and techniques of weaving. So that'll be Wednesday night at the lab for the month of February. Thank you, everybody, for coming to Wednesday night at the lab. I'm Tom Zinnan. I work here at the UW-Madison Biotechnology Center. I also work for the Division of Extension Wisconsin 4-H, and on behalf of those folks and our other co-organizers, PBS Wisconsin, the Wisconsin Alumni Association, and the UW-Madison Science Alliance, thanks again for coming to Wednesday night at the lab. We do this every Wednesday night, 50 times a year. Tonight, it's my pleasure to introduce you to Becky Larson. She's a professor here in the Biological Systems Engineering Department, and she's also an extension specialist. Becky, I get to ask you the 5 questions. Where were you born?
Outside of Detroit in Southfield, Michigan.
Southfield, Michigan. Mm-hmm. And where'd you go to high school?
Lakeland High School.
Lakeland High School? And where's that?
White Lake, Michigan.
White Lake, Michigan.
Just a little bit farther outside of Detroit.
Good. And then where'd you go for your undergrad and what did you study?
I went to Michigan State University and did all my degrees there in the same department I'm in now, but there it's called Biosystems Engineering.
Okay. So 3 bachelor's, master's, and PhDs from Michigan State. And then when did you come to Madison?
I got here just about 12 years ago, in 2010.
Very good. So tonight you're going to talk with us about climate change and agriculture, mitigation strategies for dairy. Would you please join me in welcoming Rebecca Larson to Wednesday night at the lab.
All right, thank you. All right, well, thanks for going out there in this chilly evening and making it here. Maybe smarter for those of you who stuck at home, but I appreciate those who made it here. So I have been here 12 years, as I mentioned. One of the things that I've worked on as part of the work that I've been doing is a lot of things related to climate change. So we all know that's a pressing issue. We talk a lot about it. When I first started here, I saw a lot of climate scientists speaking and left those talks pretty nervous about the future. And so I've carried that on in my research a bit, kind of working through some of the things related to climate change. But I am a manure engineer, really, like bio-waste. I deal with manure, food waste, anything that really smells bad that you probably don't want to talk about over dinner. So I'm going to share with you the perspective from a big team of a lot of different people that contribute to this. You'll find I talk a little more about manure because it's the best thing to talk about and obviously my expertise. I do want to share that I am part of a big team. Every time we present, it's not us that we're out there all the time grabbing samples. I did that once, but then you get degrees and you move on. So I also want to share that Horacio Aguirre-Villegas, he is a scientist that works in my group, and he and I have been working together for many years on, particularly on this topic. So I wanted to make sure I put his name out there as someone who worked spent more time on spreadsheets than I did on some of this. So I like to start out a lot with this particular slide. It's a really old manure hauling system, right? I like to put it up there because we've been working through these agricultural systems for a very long time, right? A lot of the things aren't so new. We used to, long time ago, they're pulling that with a tractor for display, but it used to be pulled by horses or other animals. And they would spread manure onto the fields to recycle nutrients and grow feed for their animals, and then feed that to the animals, and around we go in that circle, right? And the idea there is really like a sustainable cycle, that you're recycling those nutrients around. Things have changed a bit, but
Any idea where this dates from?
I don't know. I keep meaning to call some colleagues of mine to see if anybody can find, because you know they always have the antique tractors out there, and then weirdly this one time they had an antique manure hauling system. So, but I'm not sure. But so some things have changed. Some things in the big picture kind of seem the same, right? That same cycle is the same. The reason I want to mention that is because one of the things we think about when we're talking about animal agriculture is sustainability. Trying to go in kind of this cycle, right? We're feeding animals, we're producing manure, we're trying to take those nutrients to the crops, to feed storage, back to the livestock, etc. But sometimes this cycle gets disrupted, and maybe we lose too many things outside of the cycle. We lose too many things to the environment. Maybe some things are leading to some issues, and one of those things we're going to talk about today is emissions from these facilities, right? I'm going to talk to you and give you a little bit of background in case you don't have too much knowledge about greenhouse gases, so that I don't confuse you with some terms and some graphs later. I'm going to present you a whole lot of information about how agriculture can affect climate, right, and how we might mitigate some of those. I don't have an opinion of where we should go, right? That's kind of for society at large to decide. It's for you to decide. But I'm hoping just to provide you with some science behind the information so you can make decisions that are more informed factually, right? So I'm going to start with greenhouse gases. There's a lot of different gases that contribute to climate change, and we call those greenhouse gases, and they trap heat in the atmosphere is a simple way to think about it. I'm going to talk about 3 of those today in particular. One is carbon dioxide, CO2. You can see it as that big blue lump. We know in the US this is the biggest source of emissions that impact the climate. The other ones I'm going to talk about that are less prevalent in that pie chart overall, but sometimes have a lot of impact are methane, which is CH4, and N2O, which is nitrous oxide. Now methane, you might know as another substance that we'll use that goes to our house. Anybody think of what gas, what else do we call methane?
Natural gas.
Yeah, very good. So natural gas, methane, same thing, right? And when that escapes into the atmosphere, right, we have an issue because it increases the warming and leads to our global climate change. So these 3 different kind of gases, there's other gases, fluorinated gases that also contribute, but I'm going to focus on these 3 because these 3 are the relevant ones to agriculture. And really, methane and nitrous oxide are the bigger drivers when we're talking about agriculture than carbon dioxide. Carbon dioxide is a big player, as you just saw in that last graph, right? It's the largest amount that contributes to our climate change. The largest amount of those are released. But the potency, right, of warming from methane and nitrous oxide is higher, right? So there's a lot of ways we do this in modeling and trying to make things equivalent so we can compare them, right? So one of the things we do is we call something a CO2 equivalent, right? So we start with CO2. We're going to compare everything to that, right? So here we're going to say over 100 years, here's the global warming potential. What that means is 1 CO2 is equivalent to about 28 methane, right? So or 1 methane is equivalent to 28 CO2. So it's way more impactful. If I took that 1 methane molecule, it would have the equivalent warming over 100 years of 28 CO2 molecules. Now, is that perfect? No. Some people might use 25, some people might use 30, right? But the important thing to remember is this has more impact. Now look at nitrous oxide. Where are we there? That's equivalent to 265 CO2, just one N2O molecule, right? So that's a little bit of N2O escaping has a really big impact to warming, right? So you can kind of see how that changes. The other thing that's important to think about is lifetime. So these molecules remain in the atmosphere for different durations, and so they have more impact. So we're talking about 100-year, so this is their impact over 100 years. That's a pretty common time frame that a lot of people talk about, all of these greenhouse gas emissions and their impact. But you don't have to talk about 100 years. Sometimes people talk about 50, sometimes people talk about 10 or 1,000. So it's important to remember, if you want to compare apples to apples, as we say, you want to make sure that your horizon, your time frame is the same when you're comparing them. So they stay for different times, right? So that means if I had a methane and it's only in the atmosphere for about 12 years, a little over 12 years on average, right? And then it usually oxidizes the CO2 and can convert to carbon dioxide as its fate. So over those 12 years, if I looked at a shorter year horizon, a 50-year horizon, right? Would the impact of methane go up or down? It would go up because it's really prevalent for only those 12 years. So if I looked at something shorter, you don't have to understand all the math and how it works and up and down, but it's just important to remember as you're looking when people talking about this, carbon dioxide equivalence is when we convert these other gases into CO2 equivalent warming so that we can better compare things and understand the impact it's having. Hopefully, as I get into some data, if that doesn't make a ton of sense now, it will as we go along. So here you can see they talk about CO2 equivalents, right? These, and we are trying to look at, okay, where are the greenhouse gases over time? Where are they coming from, right? So this is kind of just another way of showing over time in the US, the majority of the greenhouse gases emitted are from carbon dioxide, right? And if we look at the equivalents, that red is the methane. So not a huge impact from methane, right? But it's there. And nitrous oxide would be the next most important gas, right? All three of those are very relevant to agriculture. What are the sources of emissions? I don't know if people could guess this right away, right? I don't know that we spend enough time talking about where are the emissions from, what are our strategies that we might want to implement to mitigate them. And really, if you see here, energy is the biggest contributor to greenhouse gas emissions in the US, right? This is the biggest contributor by far, right? So we really need to implement strategies to target shifts in energy use or renewable energies to try to impact this number. But we also should try to look at other categories like methane and nitrous oxide and places we may be able to mitigate those. When I see climate scientists talk, from when I started looking at this 12 years ago to now, it's concerning, right? We're going to have to make efforts in a lot of places. And what I hope today is that you'll think about by the end of this, how we can better not argue about what the emissions are and so much of the sources, because we kind of have that figured out, but really look at how we're going to compare strategies to reduce these, right? And so we really need to start evaluating all of the potential ways to reduce these and seeing how much they cost, how easy they are to implement, what kind of impact they have, so we can start really looking across industries, across areas in ways we can really make an impact.
Can't we just laugh off the nitrous oxide?
We could. And you'll see it is really hard. One of the hardest ones to mitigate is nitrous oxide. There's not a lot of strategies. So even if we don't want to laugh it off, I don't know that we have any other option, right? We maybe cry it off. That'll be our next one of these days. So greenhouse gases from agriculture, again, not the biggest part, right? Transportation, electricity, industry, commercial and residential use, all of these kind of energy uses and other things are bigger emission sources. However, agriculture is 10%, and we can't afford to leave that chunk out. And as we keep looking forward, you'll see they're big factors in that methane and N2O, right? Now think back to what I said to when we were looking at the equivalents, right? If we're saying one methane is 28 CO2s, if I can get rid of one of those, that's pretty big impact, right? So while they may not be huge categories in terms of the overall emissions, we may have really significant ways to mitigate large amounts of those emissions by looking into some areas of agriculture. So let's talk a little bit more about methane. Again, 28 times, maybe more potent depending upon your time frame. We're talking 100 year. It's also emitted by a lot of natural sources, right? But we're going to talk about sources that humans, that we lead to some of the emissions of, right? And so you can see here, enteric fermentation is the biggest source of methane. So what is enteric fermentation? Right, that's from cows, their stomachs, so we have beef and dairy cattle, and they're eating, you know, getting fat, having a good time, and then they release the methane, right? And so that's where we get this huge category of enteric fermentation. Now, what is the easiest way to get rid of enteric fermentation? Don't have any more cows. So I don't know if that's easy, but it's a strategy, right? The other way could be we could try to mitigate that and try to reduce some of the methane that comes from them as we produce some of their food, right? We'll have to figure which strategy out makes sense for all of us. Manure management, that's the area I work in. It's 10% of methane emissions. Not super enormous, right? Now we're 10% of 10%, right? So maybe 1% overall, but that's pretty big, especially because we have a lot of potential solutions in manure. Enteric's a little harder unless you want to ditch animals altogether, all of the beef and dairy. I would say that's possible, but we'd have to work out some protein sources and some other dietary issues. So that is a possible way to go. I don't really have a preference, but people out there have to decide what is most important to them. So nitrous oxide, that big one that has a lot of impact per little molecule, 265 times more potent than CO2, right? Hugely from agricultural soils, right? This is loss. We have nitrogen in soils. Part of the natural cycling of soils releases N2O. There it is. It's out there. We can't really stop a lot of those processes. Even if we really limited our nitrogen additions, we would still see a lot of N2O losses. Really difficult to manage those. We still have CO2 losses, right? We still have CO2 as part of the carbon that's lost for the thing, but it's not a huge port. Remember when we saw all that CO2 from energy sources? The CO2 from agriculture isn't that huge, and some of it's what we call biogenic, so it's released and regained really fast, right? I might lose some carbon and then the plants take it back up, so around in a cycle it goes. So let's talk about dairy in particular, right? So there's some kind of bigger picture about agriculture, and now I'm going to talk a little bit more specifically, and I'm going to work down until we're really in our boots in manure, where I feel most comfortable. So dairy in particular contributes about 3% of those emissions globally that we were talking about before. And the greenhouse gas emissions from dairy have been increasing over the last 10, 15 years, right? We're seeing more emissions from them. Now, is that important? Yes. We probably don't want any sector going upwards, no matter how much more milk or what. We're producing more energy. We don't want more energy produced with more greenhouse gases, right? Same with milk. They did increase production and yield. So it's important to think, do we want those going up? Probably not. Can we think of it as its own little piece? Probably not either, right? So we need to think about, why did milk production go up? What did it replace? What are the greenhouse gases from that system compared to this system? And are we making the right decisions in terms of where we're going to protect the future? Dairy accounts for a huge amount of methane. And manure management from N2O also contributes to that. So let's look at the dairy farm. There's been a lot of studies out there, and you'll notice again, greenhouse gas emissions on the left here, on that, I don't know why it's not coming to right now. The y-axis going up, we have greenhouse gas emissions, and those are CO2 equivalents, right? So in all of these graphs, we've converted the methane by multiplying it by that factor and then putting it together. And what you really find, right, on the farm, enteric and manure management are really big, and most of 72% of the emissions produced in the whole kind of cycle of producing dairy products, transporting them, dropping them off, is on the farm. So most of it's on the farm. The transportation, the retail, the consumption, the disposal, not the hugest parts of it, right? So why is this data useful? We need to kind of dissect a lot of areas and dig down and find out where can we get the most, say, bang for our buck and trying to reduce some of the emissions. This is just, again, kind of looking at it in another way. And in that farm that we're talking about when we look at it, now every farm is different, so this isn't going to be perfect, but look at how much of the farm, of that entire on-farm part, is from enteric. Like, so just the cow's production, which is a tough thing to mitigate, is already at 50%. And then the rest of it are things we have a little bit more, manure in particular, the crop production, N2O, that's also still a pretty tough one. So I also like to look at it in this way, right? When I look at a dairy farm, where are all these emissions coming from? So we have animals, they produce manure. We go to manure storage, we go to land application. So in my manure system, you'll see the cow, the CH4, if it's really big and the arrow's really big, it means more is coming from there. So we get most of it from the cow. Some of it, well, the manure sits in the barn, right? There's microorganisms in there, they're degrading the manure and it's releasing methane. Some in manure storage, we might put it in manure storage, and while it sits there in anoxic, so not a lot of oxygen, and those microorganisms are degrading it, they release a lot of methane. And then land application, we take it out, we put it on the land, we're releasing some there. But you'll see the biggest one's still manure storage and the cows, right? So let's split this up now, okay? Here is the cow. How do we deal with this, right? So actually, you know, a lot of people think the emissions are coming out the back end. We're actually about 95% of the methane is through them burping, right? So how do you think we might be able to reduce that? Now they have tried crazy things like putting a bag on the back of the cow, like some explosive biogas right on a bag. I don't know that that has worked out successfully. I don't see a lot of bagged cows out there. But there's other ways we might be able to try to reduce the methane. And so we break those down into lots of strategies. And we work with dairy scientists and they evaluate some of these strategies. So one is you can use different feeds. Certain feeds produce more methane than others. You could breed animals, so you could use genetic. You know, we're typically over time have been breeding animals to what? Produce more milk, or in beef, produce more meat, right? Reduce resources to impact. Maybe we need to put a little bit more into the genetics in terms of reducing the emissions, right? Also, keeping cows healthy, right? The healthier you can keep a cow, the more productive it can be, so then the more milk it produces, and efficiency is really important. So you produce more milk, the cow's still going to end up generally producing the same amount of methane, but if you can get more milk from it, the amount of methane produced per unit milk you produce is a lot less, right? So that's a good thing. We need to think about that two ways though. Efficiency is really great, and that we can get more milk for less methane, but if we're producing so much milk, even if we bring that down and we're efficient, it still might be too much. How much is too much? I don't know. We have to figure out strategies, right, across all of the systems to make that effective. So there's a lot of things you can implement. In each of those, they try to do studies and estimate what's going on. So like here at UW, the dairy science, they'll feed some cows, different feeds, and then they'll have these little machines that catch their breath. I'm glad it's a machine and not me that has to do that. But they'll measure how much methane a cow is producing over a certain time, right? Maybe they'll try some different genetics and see how that cow's doing. And then they'll look at, well, what do we think we can do? So with all those approaches, we think, maybe genetics, you might be able to reduce 15%, 17%, 20%, somewhere in there, right? Reduce that enteric methane. That's pretty big for how much methane we were producing with enteric, right, from the cows. We might be able to change some feeding and nutrition. And so if you really think about all of them, trying to do all of that over time, we think maybe 30%, maybe you could mitigate 30% of that methane. Now I'm going to move on to manure systems. Now manure, there's kind of 4 stages of manure systems that I like to think about. We produce manure, all animals produce manure, right? We have to collect it, whether or not it just ends up in a grazing system right on the ground, or if it's in a barn and we collect the manure. Then we put it in we could put it in a processing system. We don't have to, but we could. We could put it in storage. Again, we don't have to, but we could. And then land application. I would say almost 99% of livestock facilities land apply their manure. There's a few select ones, where they're making boards out of some of the manure, or a board that kind of looks like plywood, or maybe making pots or a few other things that they're trying to work into there. But generally, it ends up back on the field where nutrients go back into the crops to feed the animals, or to feed people, possibly. Okay, the other thing I want to talk about in manure systems is ammonia. So it's not a greenhouse gas. So why am I talking about it when I'm talking about greenhouse gases? Well, ammonia is a nitrogen that's lost. In a portion of that, we call it indirect formation, that causes N2O, right? N2O is really important. So even the little bit that ammonia is lost, and then that ammonia can form a small amount of it into N2O in the atmosphere. So it's important that we think about that in terms of the whole cycle of the system we're looking at. Okay, so let's talk about storage, and let me tell you, not all farms are the same, right? There's a whole lot of different kind of farms. I like, sometimes we try to do surveys and talk to farmers, and I think the common thing is you have 100 farms, you get 100 different answers, right? So farms they just aren't the same, they don't operate the same. Overall, in a big picture, they might, but they're using different management practices, different styles. It's interesting to me that people understand that from a perspective of other industries, right? That company doesn't produce chairs the same way this company does. Agriculture is just the same, right? And that one farm might do it a bit differently than another farm. And so generally, here's where we modeled like a conventional farm, is what I'm going to call it. It's maybe more typical, if you can have a typical farm. As you get larger, more farms use liquid or slurry manure, so it's not as solid. Sometimes you might see big stacks of manure, that'd be solid manure. Liquid manure would go in those big storages. You might see tankers, you might smell it when they're applying it, right? That's probably the most common reason people recognize it. And when we have those storages, what happens is we store it over time. In Wisconsin, 6 months, right? What 6 months would we store it over?
Winter.
Yeah, because there's no crops growing. They don't need the nutrients. If we put that out there, what's going to happen?
It'll just run off with solid.
Yeah, it'll land right maybe in our streams, depending upon the field, but you get a big runoff event, the snow melts, it doesn't infiltrate, away it goes in other places we don't want. So one of the difficult things in dealing with some of these issues is storage is really great because it allows us management flexibility to apply manure when we're not going to create a lot of water quality issues. Now, on the other hand, we store manure and we cause all of these emissions because we're storing it in a way where it's anaerobic. So what do we do there? What's more important to you, clean water or clean air? That's a pretty tough decision to make, right? So we got to try to look at, well, I would say I don't want to get rid of storages. I don't want to lead to runoff events and lots of manure getting applied in the winter. For decades now, people have been trying to work away from that. So maybe we need to look at ways to mitigate those losses from storage as we store it. Solid manure, you get the same thing. You can still lose emissions, but generally when you're piling it up, it doesn't have as much liquid, so more air can get in there. But what happens here, right? We still have a lot of nitrous oxide emissions when we apply this. And what did we have here? Maybe a little less nitrous oxide emissions when we had that liquid. So again, people might try to say, oh, let's have a small farm, let's have a big farm. But really the management practices you use end up really driving what's happening and then the strategies you need to implement. So I'm always trying to convince people that size of farm is not the driving thing of how impactful it is to the environment. The practices you use are the things that drive how impactful you are to the environment. Now, that being said, large farms, if they're doing it wrong, have bigger potential to cause more damage, right? But then again, they also have more resources. So really, I don't like to think of big farm as worse or small farm as worse. It's really how you manage a farm that determines its impact. And then whether you use solid or slurry manure, you just have to manage it differently, right? There's different ways to mitigate the different issues that might arise, whether that be more methane or more issues with hauling daily. So one of the things that I think of in manure systems is, well, one great way to mitigate that is to implement some processing. And so I'm going to talk about 3 of those today and try to get away from some graphs and maybe show you some pictures for a little bit, mix it up. So the 3 that are probably most common and have the most impact to greenhouse gas emissions are composting, anaerobic digesters, and then something we call solid liquid separation. So composting, maybe that's one people know about. Have a lot of people seen a composting operation? Know anything about that? Nope, maybe. So composting, a lot of times you might see a more common method, which is like windrows that are lined up. I think I had pictures of those right here, right? People out in the farm, you're putting the manure, mixing it with other things. You're letting the natural microorganisms degrade the manure, right? And we're producing a product that is much less in volume and has less pathogens and odors and other things. We have in-vessel composting systems that are a little bit fancier, where the manure goes in, you mix it with some other things to get the right conditions. And generally we have aerobic microorganisms. And so those aerobic microorganisms, as they break down the organic matter, they're releasing mostly CO2, right? So what's happening here is you're reducing the amount of methane that would be lost from manure, and you're losing that carbon as CO2 instead. How does that have a big impact? Remember when we said methane was 28 times of 1 CO2? So if I can drive a carbon into producing CO2 instead of methane, we can have big mitigation or reduction of the emissions impact, right? So that's really great. Also, you reduce a lot of that nitrogen loss, right? So you can actually you might increase ammonia, and N2O emissions. So here again is that, I'm reducing methane, but I might be increasing N2O a little bit. In the end, when you look at all of the emissions, this composting drives down the emissions overall in total, even though N2O might go up a little bit. I lost a picture here, but digesters are the next top thing I'm going to talk about. And if you've ever seen one, they're like a big tank, right? Sometimes they're underground, sometimes they're above ground. Sometimes they have a little window in them. I don't know why. People always want to go see what's inside. What do you think looks like inside that big giant tank? It's like a shit slurry, right? So there you have a bunch of manure. It's in a tank. And what the tank is doing is you have all that manure in there and you're collecting the gas that's produced. Now in there you're limiting oxygen. So anaerobic microorganisms are taking over and they're producing a lot of methane. So then we're going to capture that methane and use it like natural gas, right? So we can use it in all the applications of natural gas if we scrub some of the other things in the gas. So there's a lot of agricultural digesters out there. You can see in Wisconsin, we've got a lot of them on dairies. They can be on any livestock facilities. They can also be on human waste, right? These are agricultural digesters, but we have them here in Madison and many other places at our wastewater treatment plant, right? The same gas is being captured from a landfill, right? So there's a lot of ways that we collect methane out there. In Wisconsin, we have about 40 digesters operating in the state. And mostly they're on larger facilities, mostly because of economies of scale and costs that are associated with implementing that technology. But, oh, here's the picture. I just got it out of order. So you can see that top one is what we call a completely mixed system. It's a digester. You have mixers in there. You're capturing the gas in the top, the biogas, which is mostly methane, but also has CO2 and some other impurities like hydrogen sulfide. And then here's the bottom. That's a plug flow system where it's flowing through a system underground. Still, you know, that it's just holding that in there for a certain amount of time at a certain temperature so the microorganisms naturally within there can produce methane. And then we capture that, and we can use it for a variety of end uses. We can have really small-scale digesters. We can have dry digesters where you're putting in feedstocks that are more dry, like dry manure that we talked about before, or maybe food waste. All kinds of different waste can go into these systems, organic waste, and then we capture the gas. So we can make electricity with these systems, or we can do something like what is more commonly transitioning to right now, where you clean and remove the CO2, and then you inject that into the natural gas grid, or you compress it and can use it for vehicle fuel, right? So this is the small system that used to be out at the landfill, but it's the same kind of technologies. And they've even gotten a bigger one, so you can run trucks off of it. You could run tractors. There's a lot of places in Europe where they run tractors directly from the gas produced from a digester. We could also use a separator. So one of the things that we have at farms is we have the manure come in. It'll go into this separator, and this one's pretty simple. It's a screw press, maybe the most common kind of separator you see. And it'll take the manure and divide it into two piles, right? Now I've got a solid manure and a liquid manure. I can have a lot of separators or a lot of fancier membrane separation technologies that might divide that into more piles, and then I can more effectively manage those. We can use centrifuges that really can have a high efficiency of removal of solids. Rotating screens, this is one where it goes into that screen and the baffles move it along and the solids stay on this side of the screen and the liquids move through the other side. We use these incline screens to remove really fine particles. All of this could be in one building, and it might go through one and the other, and the scent in there is really nice. So, and then we have presses that can remove some of the moisture. So after we look at a bunch of these systems and we measure the separation efficiency, what we find is when we implement these kind of strategies, I'm going to skip over to this one on the right here for time. But say we have this raw manure, right? And this is naturally what it produces for emissions and storage, and then when we land apply it. Now, when we put in a digester, which is this AD system, right, we really reduce that methane. Look at how big that reduction is. Because we've taken the methane, we've captured it, and then as we combust it in one of those end uses, we convert it to CO2. So we've really reduced that. Now, in addition, we might use that instead of fossil fuel, right? So some people also like to take the credit, as they call it, where no longer you're producing the energy from a fossil fuel, which has a really big release when we saw at the beginning there, right? And you're now using this energy that's more renewable. This is the solid liquid separator. When we modeled some of that recently with some updated data that we saw, that actually produces very little methane, really reduces a lot of the emissions, even compared to a digester. A little cheaper to put into than a digester. So there's a lot of options, especially on these bigger farms where they're putting them in. Now, do we see a lot of these out there? I would say these are only ending up at farms that are maybe 800, 1,000 head or bigger. You don't see a lot of these technologies at smaller farms. Composting is probably what you'd see at a smaller facility. That also has impact. Now again, I want to talk about something else. Remember, the emissions went down with these processing for greenhouse gases, but what happened to ammonia? With digesters, it went up. So it's not a greenhouse gas, but it does have some indirect formation of N2O. But ammonia is not a great thing either, right? So again, there's some trade-offs here and that we have to continue to find strategies to mitigate some of the unintended consequences that might happen from some of these things that we implement. So manure storage is the next part. So we have manure processing there. So we can manage the cow a little bit to mitigate. We can manage the manure with processing. We can also manage it a little bit with storage. Again, we want to use this manure storage to reduce issues when we apply manure onto the land, particularly with water quality. It allows us a really flexibility in timing and in a limited time when producers have to put manure out in the fields. So look at this particular picture that was taken in Pennsylvania. The storage is caught on fire, right? Why is that? Because it's producing that methane, right? And that's not common. I wouldn't really worry. That's a weird situation that happened. But it just shows the methane is being produced. Now we can capture it with a digester. But the other things we can do is, I'm going to skip this for a second, is go to covered lagoons, right? So we can cover the storages to keep that methane from being lost, and we could capture it and just burn it, right? So again, we're taking that methane, converting it. Or we could just use other kinds of covers, straw, plastics, other things, just to keep the methane from being lost during that storage duration. So that could have a really great impact there. I'm sorry to the folks in the back. I'm going to go back up for a second. There's other things that happen, though, in storage where we might lose N2O in these things. And so if you can promote like a crust formation or other barriers, we can also limit that from happening, from losing from liquid storage. Dry manure in general has less losses than liquid storages. And if we move to something like aeration or composting, we can even reduce those further. Okay, I got those a little out of order. Okay, so the last step now is manure land application. So here's probably, so remember I showed you that really old manure spreader? Is this a whole lot different? This wasn't taken too long ago, not really, right? But there are ways that we can reduce the losses from land application. One of them is this injection system, right? So what we can do here is we can take manure, put it into use this toolbar, where it actually opens the soil, puts the manure in, and covers it, and so you can't even see the manure once it's in the thing. So what do you think impact that has, right? Well, one, runoff is way reduced, right? But also, it reduces the losses of methane and ammonia that can then form N2O. So we have some mitigation strategies there. The downside is maybe now you could end up with more N2O produced because more nitrogen is trapped within the soil system. But N2O is really hard to mitigate, right? So it's really dependent upon the wetting cycles within the soil and really hard to change. We do see that some additives, we've started doing things with biochar and other things where you might be able to add that and mitigate a lot of the N2O losses. But we're still managing our way through that. I want to say farm size again. I know everybody wants to push for that, and then we tried to look with some surveys at what different kinds of farms were doing, right? So how were they managing their manure? What were they doing at different scales? What are some of those practices that they were using? And, intuitively, people might say, well, a large farm is probably going to have a really big impact. And I would say that's possible. So, but per the amount of manure produced, we took a lot of that survey data and we put the most common, what we call a reference for that size farm in the middle. And then we took practices that would reduce their emissions that we saw out that people were using, and then some that would increase emissions that people might be using. And what we found is in every case, there's a lot of practices you can implement to really change those that they're already using that change the emissions. Now, these aren't even implementing some of the strategies that might be out there to really reduce those emissions. And here, you see that large farms are really small because in this case, we use those processing systems, right? So if you're a large farm and you're not using those processing systems, you're probably having a pretty big impact. But if you are using them, then, well, maybe your impact is much lower. Now, why aren't we using them here? Well, we don't see them very commonly, but we absolutely could integrate them into other size farms if we wanted to, right? But what does that take? some cost. There's some cost to that. So for me, I could figure out, well, it's going to cost about this much money to reduce the impact this much. Now, we can come up with a lot of those terms, and in the future, I hope that we'll be able to start comparing them. Like, well, is it cheaper for me to switch from coal to solar, or is it cheaper for me to put in a digester and reduce that emission right there, right? So in a bigger picture across all systems, how can we really achieve those reductions? I just wanted to add this slide to show that Horacio also models a bunch of organic dairies, right? There's a lot of different systems. Strangely, when we do these for greenhouse gas emissions, the emissions are pretty similar from more conventional non-organic farms to organic farms. And that's a lot driven by efficiency. So looking at this is per fat and protein corrected milk. So the amount of milk you produce, your emissions divided by your amount of milk you produce. So if you produce a lot of milk, your emissions are going to go down. And so the other thing I want to mention is they might look the same, but there might be some other areas, right? How I was talking before, how do they compare in other environmental impact categories that we also have to think about across. And that scientists, we choose particular parameters to look at, right? If we did emissions based on cow, organic dairies look a little bit better, right? So what is important to you is the kind of information you need to seek out, right? That you might need to pay attention to. You know, does it use more water? Does it, in California, that might be really important, right? Here, it might be more important that we use strategies that don't impact our groundwater, right? So there's a lot of things you need to think about that are spatially important and then important to the people who live in that area. And so I would say push researchers. If we're only giving you one number and we're not saying that there's other ways to look at things, you might want to dig a little deeper. So one of the last things I want to say is that there's a lot of mitigation strategies, and we use all of these kind of, this is like a weird, I call this like a weird Tetris graph, where you can kind of see how much you can reduce that by integrating all these practices. So this one was relative to the organic dairies and how we can try to mitigate some of the emissions. Now some dairies have thought, well, let's try to get to zero. Let's try to get 100% reduction of our emissions. You'll see a lot of these combined strategies might get you to 40, 50%. So I would say, you know, while we should shoot for getting to zero, maybe the cost and the difficulty of implementation, bringing all of them down to 50 if we want to continue to enjoy some of these products would be a great strategy. All right, so just a few things in conclusions and then any questions or thoughts you might have. One, we definitely have greenhouse gas emissions from agricultural systems, and they absolutely contribute to global climate change. Mainly, we're concerned with methane and nitrous oxide and their contributions. There's a lot of ways that we could mitigate those in all different areas of a farm. It's very specific to the farm. And one thing I didn't mention that I should mention now is even if we come up with the strategies, there's a whole lot of other things that need to go in to helping farmers implement those strategies too, right? They have a lot going on, and adding this new part into it is complex, as you can see here. And so there's going to need, even when people decide that they want to make some decisions, it's going to take a little while to get those underway. Different farm systems have different strategies, and we have to be careful of unintended consequences, right? And when we might try to mitigate emissions here, but then have a negative impact in another environmental category. And then, you know, scientific data, assumptions can lead to misleading conclusions. So make sure you understand what some scientists are assuming behind some of their work as they present it, right? We have lots of additional resources. If you found something to be interesting and you want to know more about it, hopefully something. If not, well, then you're free from any more reading. But at the Learning Store, you can either go to the collections of Farm and the Environment or Manure. You'll find all of these fact sheets. We had, through a big dairy project run by Matt Rourke, we put about 13 different fact sheets out there that detail a whole bunch of this. We have courses in my own department that we've developed for online learning if you want to learn more about it. And one of my favorite resources is this virtual farm of a dairy that we built with Penn State. And so on this particular farm, you can go into a map and click on stuff and kind of navigate your way through your own farm and try to learn about it. And we did 2 different farms. One is about a 1,500 cow farm, one is about a 150 cow farm. So you can kind of see some of the differences that might come into play and the different strategies you might use for those farms. Just because at those sizes, they might implement different strategies, not because the farm size itself is impacting that, but just the resources and scale might change the management practices that they would most likely use. So I think that's a really cool place. And if you're ever wanting to talk about this yourself, in the resources, there's a cool place to get a bunch of graphs and pictures that you can just pop in slides or look through or whatever you might want to look and find. So again, I want to thank you for listening, and I'll happily take any questions. And I will also give one last shout out to Horacio, looking not manured in that picture, but he really works hard on putting a lot of these pieces together to formulate a bigger picture while we grab the manure samples out in the field and contribute to the big picture. So thank you.
Line. We'll start with that, if that's okay. Have you looked at seaweed as a cow feed?
I have not, but I know some others have. We actually have a project using algae right now to try to look at algae integration, but I know that some others have started to look at many different feeding supplements and different feed sources in terms of the production might have lower impact, as well as it might produce lower impact from the emissions from the cow. But
So I didn't know if you had
one.
a chance to read that one from Western Australia that I included in the missive yesterday.
I did not. I did not.
Okay, because
But if you have information, feel free to share it.
No, I just was surprised that when I'm writing it up yesterday here, this thing was dated February 2nd, because Perth, Australia is like 12 hours ahead of us. And
As far away as you can get.
Yeah.
yeah, best place on earth. Other questions?
This is probably out of your bailiwick technically, but do you know anything about these experiments? I've read about them making synthetic meats, and supposedly they've been quite successful. I think that would certainly go a good step towards solving a lot of these problems.
Yes, it's very possible. So I haven't done a lot of research into the environmental impact of them because I think they're still working out how to, so they produce them. But I think the energy and inputs at this moment are probably highly intensive to produce the meats, but I don't know that for sure, but I would assume so. But I think they're on the cusp of potentially, if we could make them, and then you always have to work on the efficiencies of a system. I'm guessing they could get to a place. So even people used to say, well, could we produce milk, without the cow and kind of make the rumen functioning without having to have an animal there? And I don't know if those will pan out, but I think they're definitely avenues to look into to see if we can get some of the products without having, can we result in something milk produced with less impact. Mm-hmm.
I'm kind of wondering, the data you found, like in the U.S., how does that compare with like EU or South America, Australia, Japan? Because all these countries which I mentioned, they do have dairy.
Yep. So in a lot of like Europe and other places, the emissions are pretty similar. The farming systems aren't so different. So when we were looking at the emissions that for some of these studies produced in different areas, they're not hugely different from, say, Europe to the US, where we have some advances in genetics. Sometimes the low efficiency of some places, like I work in Africa sometimes, the really low efficiencies of the animals might lead to more impact per unit milk produced. But again, it's that impact kind of category, right? So they have introduced more things like digesters and other things that are driving down some of their emissions. in European countries. So they've maybe implemented more strategies to mitigate there. But I would say overall, a lot of them are still on the same playing field. You might see small numbers, but then again, small differences can, over a large amount of cows, can have a decent impact. But I would say the strategies are a little different. So also people might point to a lot of times like New Zealand, who has a lot of grazing. And I would say just like conventional systems, they have a different problems to solve. So there you have less control of how the manure is applied and how the urine gets into the system. So you might have more N2O production, a little less efficiency in some other areas. So then you're just, this overall system might not be worse, you're just having to work on different problems, right? So I would say nobody has a system thus far that looks like, hey, this is the ticket, right now that it's way better. I would say the places who are really reducing, the farms who are really showing some impact are the ones trying to look a little bit into the reducing enteric, and then if you can put a digester in, you have a huge reduction, or a separator and a huge reduction in your emissions. And in California, they've actually had a lot of impact by implementing those strategies based on, they'll give you funding to implement those technologies based on your actual quantified reduction of emissions. So trying to implement some new strategies and ways to make that more effective. Mm-hmm.
I'm trying to think of a way to ask this question in a succinct way, and it's like a double question, I guess. Is there a difference between dairy cows and then beef cattle? Because it's all about dairy cows. We're in Wisconsin, of course, if that's the reason. But then also why it's just on cows that this is being talked about, and like, what about pigs or chickens? Do they not produce the same thing?
Yeah.
Or?
So enteric would go away. So that big enteric bar from the other animals goes down. But you still lose methane and nitrogen from their manure systems. So the manure systems of those animals are still impactful, and the feed production and the energy use, so that's there, but that enteric bar goes to nothing because that's a system related to rumen animals. So, but beef compared to dairy, there's some beef studies out there, and sometimes we actually mix them because some dairy actually ends up being sold as beef, and there's some interesting things that kind of happen there. But generally beef animals still have that enteric production. It'll be a little different based on their feed. Their feed's different. You would feed a dairy cow a bit different than you would feed some beef animals. So I think their emissions end up being a little bit different there, and you're managing the systems quite a bit different. So I would say like a lot of beef farms, unless you're on like a feedlot or something, you might be grazing a lot of those, or something where you're not collecting and storing manure. So your emissions might be in different places, and so you'd probably have different mitigation strategies for those as well.
Question from online. I have a side question concerning underground coal fires that have been burning underground for decades, as to what is their contribution to greenhouse gases.
I don't know that. I would say anything that's producing, I'm sure there's some emissions coming out of those systems from what they call rogue emissions that would be lost anyway, and then the burning of it is releasing carbon. So you are getting emissions to that. How much weighs into that big picture? I'm guessing it's not gigantic, because when I look at the charts, that doesn't stand out to me as being one of the things that popped out as one of the big leaders, but they obviously contribute. And if they might lump that in with all of coal fossil production as part of the system of losses they have, but I'd have to read a little bit more about that. But it's a good question. All of these pieces, when they account for them, it's important to kind of know which ones they're talking about, and hopefully someone that does more bigger picture emissions would hopefully be able to answer that with a better quality than me.
I'm not sure if this question could apply, but I was thinking, I mean, I know ag has gotten a lot of bad rap, you know, creating a lot of greenhouse gases and everything else. But when you show that one graph, which showed, I think, 10% is from agriculture, and then like 20% is from electricity, and then transportation is another 28%. Since we're trying to push electric vehicles a lot, have there been studies done that basically can figure out, okay, all these cars that burn gas and diesel, and when you replace them with electricity, and how much it's going to take to actually, you know, create the electricity for the replacement? Is it going to be more or less? Any idea?
I think I think it's less, but then your source of energy is important. So very interesting, Horacio showed me this cool graph that I'm always like, wow, everybody should be able to see this. Where you're at in the country has a very different grid makeup, energy grid makeup. And we, in particular, in this area, have a lot of fossil fuels in our grid. So an electric car here wouldn't have as much reduction as one implemented on like the northeast coast, where they have a huge amount of renewables in their portfolio. And so an electric car there would actually have a bigger impact than one over here. But I do believe those studies are out there. Maybe one day you'll have somebody come here and talk where they show what the reduction is and how that's affected by where your energy comes from. So I would say we want to convert to cars that are using electricity, but we also want to convert the electricity to renewable. So I think for me, it's all about the cost thing. So it looks like, you know, like solar is it's really looking cost effective at the moment. And so when I see that big energy thing, my natural tendency is to say, well, we need to do that. Then when I see a climate scientist talk, I say, we need to do that. We also need to do this. We need to do it all because we're losing ground here pretty quickly. So I guess in the end, we'll see. I also think maybe sometimes they talk about the impact. So some things we can implement quickly and have big impact, which we probably need to start, well, we absolutely need to start doing. And then some things will have a longer term impact that might take us longer to get them all integrated.
Plus, I heard that in the last 2 or 3 months that in colder weather, if you recharge your electric car, I think it loses like 30 to 40% of the charge. So in our area, that would, in a way, require double the energy when you think about it.
Yeah. And so I think they have a lot of studies out there how, and I think they take into account the efficiencies of the systems, and you can see like they'll put this graph, and then you know how I had the reference of the low and high, they'll be able to show you like, oh, for an electric car in cold weather, the emissions are a little bit, the reduction isn't as great as lower weather, but yeah, it's a good, it's pieces we need to think about when we're comparing all of these things. But your questions are great, and I also think, it is interesting to me what gets a bad rap and what doesn't, and I don't try to influence that. I just want people to see like, hey, we might need to give more things a bad rap, you know, if we're playing on equal ground. So maybe that's the reality.
So our speaker last week was Bruce Johnson, and he talked about electric vehicles, and he addressed that, about the 20% loss as temperature goes down. But he also pointed out, you know, he asked the question, does your gas engine get better or worse efficiency as it gets colder, and it goes down also?
Yeah, that's
so
very
that
true.
apples to apples thing is a big deal.
Absolutely.
Randy Jackson was here at middle of December talking about Grassland 2.0. Where I grew up in Dixon, Illinois, there were cows 60 years ago. There aren't anymore. And I'm wondering what you can tell us about the changes in soil composition, tilth, health, whatever we would like to call it, 100 miles south of here where there's hardly any dairy cows compared to here, and 100 miles north where there's a lot of dairy cows.
Yeah, I would say I probably can't speak too well to the soil differences, but I do know from soil health that adding organic matter is a really important thing. right? It's really valuable to be adding some organic matter to keep soils healthy. Now you can go too far, and then you end up with soils that have too much of stuff, and when you have an overabundance, it increases the losses of things. So I would say you see some areas that really need organic matter, and some areas that have had too much of it, too much manure. And so it's really, maybe you're getting at that it's spatially dependent a little bit on the impacts.
Yeah, the other
and
thing
it does
is,
change the soil, but yeah, go ahead.
the other thing is almost everything is corn and beans in Lee County where I grew up in Illinois. And yet when I was a kid, we made alfalfa hay, we made sweet clover hay. The only thing that people are growing now that I've seen driving in the countryside is horses, raising horses. And that's not going to be enough compared to 1.3 million milk cows in Wisconsin. So that's another thing when I see your composting and I think about, wow, what this can do for the soil here in Wisconsin. It's not only the compost, but it's also the alfalfa and the other forages that we're growing because we're feeding cattle. And I think that's part of what Randy was getting at with his grassland 2.0 is that perennial grasslands and cattle can do things in a way that's less detrimental than row crops.
Yeah, certainly.
Okay, a couple more questions.
I was wondering if you could say something about the experimental energy plant that works with agricultural waste, the one I'm talking about, the one that's just outside of Oshkosh.
Yeah, so I'm not sure, maybe it's the dry digester, or maybe it's one of the wet digesters.
I think it's dry, their process.
Yeah, so that dry digester, I probably went too fast over that. I was realizing I was talking too slow. That dry digester is pretty cool. It's got these different bays in it. And so you can take the feedstocks and put them in the bay, and then they seal the bay up. And then the microorganisms that are natural in manure, so a lot of times they'll mix manure, or they'll take a part of what they took out last time and mix it in with the new feedstocks. So the microorganisms break that down, and they produce the biogas with the methane in it. So they collect the methane there. And so this is actually some pictures from that facility, and they take some manure, they take food waste, they'll take some municipal organic waste, and they'll blend it all together, put it in a bay, and I think they have 4 bays. And so each week they'll take out one bay and close it back up and fill it back up, and so they run for about a month. And you've got some recirculation of some liquids in there. They capture the gas, and then the gas can go for a variety of things. I think right now they're producing some electricity, but you could also do the same thing, clean it up and put it in the pipeline, or compress it, or burn it for heat. So there's a lot of options there.
Is this the place that's within the Oshkosh city limits?
I think so. So this is right with near the university.
Right.
There, yep.
Because there's also something out in the countryside where they have a plant too, and I was wondering about that, how successful that's been.
So they had a digester similar to this one. I don't know if that's like an above ground tank system. I don't know if I'm getting it wrong. I'm sorry if it's not the one you're talking about, but these have been pretty effective in terms of their mitigation strategies. They're costly, so they're a lot to invest in. And when we just produced electricity from the gas, I would say their payback was tough. It was hard to make them financially viable from selling electricity because the generators were really expensive to run. The hydrogen sulfide in the gas is really corrosive. And so now that there's a new system where they're able to clean it up, put it in the pipeline, and they're able to get the LCFS credits, the low carbon fuel standard credits that originated out of California. I think the area has grown a little bit bigger. And the RIN credits, the Renewable Identification Number. So that's a US EPA. So as you produce these fuels now and you clean them up and inject them, you get additional benefit from those 2 crediting things, like environmental credits almost. You can think of it kind of like the carbon credit market that used to exist. And so they're able to gain the benefits from the credits from those for each volume of biogas they produce. And so those are really valuable right now. And so we're seeing the drive in new digesters going in and old ones making more money with those policy changes that are driving a lot of this new development.
This might seem like a silly question maybe, but I mean, I'm realizing like there's a lot of milk being produced, isn't there? And I just think, I never think about milk. I drink a lot of it even still at my young age. I was wondering how much milk would you know is used for just people drinking it like me, or like used otherwise baking?
So it depends upon the location. In Wisconsin, I believe it's somewhere upwards of like 80 or 90% goes to cheese production. Something crazy in our state goes to cheese production. There's a lot of other places where like they might produce it and then send it elsewhere. So export it either as, fluid milk or as dried products, or they might capture, there's all these side products too that they might make and produce for everything. So I know that there is a lot of exports of it in certain places outside, but I know in Wisconsin, I'm pretty sure it's a crazy amount goes to cheese production, which is, I also like milk. But
Yeah, I looked up a lot of that last night writing
Yeah.
the missive. So the National Agriculture Statistics Service, NASS, will help you a lot with that.
Yeah.
Online, Diana noted that according to the Google, Dane County currently gets about 45% of its electricity from renewable energy sources.
Yeah, that's great.
So if you're driving an electric car in Dane County and getting it off the grid, you're doing pretty good. Sandy notes that Dane County applied to join the EPA's program after the 9-megawatt solar energy project at the Dane County Airport went online late in 2020. So that supplies about 40% of the renewable energy used for the county operations. And then another question here. This question concerns those that would be small, that is family farms, to medium-sized farms as compared to large corporate farms. Are there any cost-effective aerobic digestive enzymatic approaches that would be available, or are these not really being of concern as the feed of dairy cows is quite a bit different from beef production? I might have already addressed that a little bit, but
Yeah,
wanted to
I
ask
would
you.
say, so I also am like, well, family farms, there's a lot of big farms that are family farms, and there's a lot of big ones that could also be owned by bigger groups. Yeah, I would say mostly small farms are family ones though, so that's probably correct. But the use of the products, or the processing options for smaller farms, definitely composting. It's a really low cost way. That's an aerobic microorganism that breaks it down. Was she asking if there's an aerobic or an I think an aerobic.
Yeah,
but
specifically aerobic.
yeah, so composting is an aerobic. You can aerate things, but it generally takes a ton of energy to aerate manure, so I don't typically recommend that. We have really simple separation systems, so I talked about some mechanical ones that are costly to implement, but there's really simple things where you let, like, you have a little basin and you let some solids settle and then you leach the liquids off. Or, even in like Uganda, I see that they design things like they might have some concrete running so the liquids might drain off of a little pad area where they have some animals and the solids might stay there. So there's really low cost, simple ways to try to separate manure into different products, and we saw in those graphs how big of an impact that has. And so and composting, I think, is a really low, there's ways to get into that very low cost. There's expensive ways to get into it, but you could also do really low cost, low labor systems.
Well, thank you very much
Yeah.
once again.
Great. Thanks for
Appreciate
coming.
your talk. Thank
Yeah,
you.
thank you.
Uganda is a place in Africa where you did your work.